Okay, so this is my video number 21. I'll talk on convergence test. I'll talk on convergence test. Convergence test. Okay, so if a series, let's say if a series with positive terms, a series with positive term, then either this series converge or diverge. Yeah, converge or diverge. So that's what we are looking for. We are looking for, given a series, we want to determine whether that series converge or diverge. Okay, so what we have known earlier that this series, this series diverge, but this series, this is converge. This will prove later. We prove this later. This one we already know. We have proved this. Already proof that series diverge. So we will use these two series as a comparison to determine other series, either the other series converge or converge or diverge. So let's see the comparison series 1, okay, or comparison test 1. Comparison test 1. We have two tests for comparison. Number one, if this series convergence, if that series convergence, and we have un, which means each term of that series with that condition, then we have un also converge. Okay, in short, I can say if you look at this inequality, all right, we can see that Vn is bigger than Un. So if the bigger series converge, if the bigger series converge, then the smaller series converge. So this bigger series, we already know the properties. Okay, we already know. We may select the known series with the convergent properties or convergent behavior. Then we can determine un converge. Now un in this case is the one that we want to determine. This one is we want to determine. We don't know yet the properties of that. We don't know the behavior of that. All right, we want to determine the behavior of that series. Okay, and then this is the first case. All right, the second case, if un divergent series, and we have these properties Vn, then Vn diverge. Okay, for the divergent case, we know, look at this, un is smaller than Vn, so we may say that for the smaller series diverge, if the smaller series diverge, the bigger series also diverge. Okay, so this is the one that we want to determine. this is the one that we select. We know the behavior of that series already. So this we call it as a comparison test 1. I'll give you an example later. Now for the comparison test 2, we have comparison test 2 and comparison test 2. Okay, if we let Vn and Un series with positive terms. Okay, series with positive term. Okay, series with positive terms. And if we take the limit of the quotient Vn and Un, n goes to infinity, if this is equal to some number which is positive, then those series Vn and Un diverge or converge together. Diverge or converge together. What does it mean? So it means that, let's say we want to determine Un and we choose Vn. Okay, Un, the one that we want to determine, Vn we want the one that we choose. We take a limit, and having that limit is positive, then if we choose the one that we choose diverge, then the one that we want to determine also diverge. If the one we choose converge, then the one that we want to determine is also diverge. Okay, so if L equal to 0, in this case we cannot say anything. Yeah, no conclusion. No conclusion means we still don't know the behavior of the series that we want to determine. Yeah, we might need another test. Now let's see some example. Okay, let's see example how to use the test 1 and comparison test 1 and comparison test 2. So let's consider this series n over 2n squared minus 5. So if you look at this series, look at the terms there. All right, so the obvious choice is 1 over n, because you take the highest order for the numerator and the highest order for the numerator. So we have n over n squared, so that gives you 1 over n. So this could be the best choice for us to determine whether our series converge or diverge. But we know that this series diverge. Okay, we know this already, but this one we want to determine. Now by looking at this series, look at those things, look at the terms inside there. So we have n over 2n squared minus 5. Okay, okay, this I can write this n over 2n squared minus 5. No, 2n squared minus 5. 2n squared minus 5. Look at the denominator. 2n squared minus 5. All right, this is bigger than, or this is smaller than 2n squared minus 4, right? And you can proceed this. This is still less than 2n squared. So if I inverse this, which means 1 over 2n squared minus 5 will be greater than 1 over 2n. Okay, what we want here is n over 2n squared minus 5. So if you multiply both sides with n, so I got n over 2n squared minus 5 greater than n over 2n squared. This one is 2n squared. Alright, so therefore, I can write this part here, n over 2n squared minus 5 greater than n over 2n squared, which is, this is 1 over n. So look at the comparison test 1. What we have, if un less than Vn and Vn diverge, okay, if the smaller series diverge, then the bigger series also diverge. Un here, okay, then the bigger series also diverge. So this is the comparison test that we have. If the bigger series converge, then the smaller series converge. If the smaller series diverge, then the bigger series diverge. Okay? So in this case, we know that 1 over n is a divergent series. 1 over n is a divergent series. So therefore, in this case, since 2n over n squared minus 5 is greater than 1 over n, and the smaller series diverge, then we can make a conclusion that, so therefore, we have n over 2n squared minus 5 here also diverge. Understand? I repeat this. Okay. So this is the series that we want to determine. Alright. The properties of that we want to determine whether it's converge or diverge. By looking at the each term of that, we have n over 2n squared minus 5. By looking at that, so the obvious choice we might think of is 1 over n, because you can cancel out, just take the biggest there, and the highest order for the denominator, then you have n over n squared, just cancel out, so you have 1 over n. So our choice is 1 over n. So we know that the series 1 over n is diverge. Then you need to rewrite those things so that we can write this up to the one that we choose. Okay, for this case, it is obvious that because 2n squared minus 5 is less than 2n, if you inverse that, so we have 2n squared minus 5 is 1 over 2n squared minus 5 is greater than 2n squared, and you just multiply by n. So we have those inequality. And then on the right hand side, this is just 1 over 2n, sorry. This is 1 over 2n. And we know that 2 is just a constant, just give no problem with this. So, but we know that the series 1 over n diverge. This is from our previous knowledge. 1 over n diverge. So therefore, we can make a conclusion that that series also diverge. Okay, so I hope you can understand those things. Now let's see a second example. For the second example, if I have an example number 2 here, 5 over 2n squared plus 1. Okay, 5 over 2n squared plus 1. We want to determine whether this series converge or diverge. So the best choice might be 1 over n squared. 1 over n squared. This is the best choice to choose. Okay, and we know that this series converge. Now, how to get there from there? So we have 2n squared plus 1. Alright, this is bigger than 2n squared. Correct? This is correct. Now, if we inverse this, 1 over 2n squared plus 1. This is less than 1 over 2n squared. Alright, then you can multiply by 5 both sides. You got 5. We got 5 there. So we have this. So 5 over 2. So I can write this 5 over 2. This is just a constant. Then we have 1 over n squared. Now 1 over n squared, if we take that as a series, so we have one series 1 over n squared, which is converge. What our test say? Okay, what our test say? Our test say that if un less than vn, okay, and if the bigger series converge, so which means if vn converge, then un converge. Okay, in this case, un is the one that we want to determine. Vn, that the series that we already know the behavior, which is converge. So if you look at this, the bigger series must be greater than the smaller series. Am I correct? Yeah, I think yes, we are correct. I'm correct. So if the bigger series converge, then the smaller series also converge. So if you look at this, I think this is should be correct. 2 over n squared plus 1 greater than 2 over 2n squared. If you inverse those things, it's less than. So we can see that those 1 over n, we can consider this as a v. Alright, we can consider that as a u. So since 1 over un converge, so therefore 5 over 2n squared plus 1 also converge. Okay, so I hope that clear. The point that I want to stress here is that, okay, we have to determine, we have to recognize which one you want to find. We want to determine the behavior, and which one we already know the behavior of that series. So in this case, okay, if un less than vn, in other words, series un smaller than series vn, and the bigger series we know the property which is converge, in this case converge, all right, and then the smaller series should be converge, should converge as well. So therefore that series converge. Or you can use the comparison test too. Okay, if you want to use the comparison test too, if we take if you take a vn or using comparison test 2, if you take vn as 1 over n squared and un as 5 over 2n squared plus 1, okay, then the limit of un over vn, this is equal to limit, our un is 1 over n squared, vn, you can inverse that, we have 2, correct, un over vn, so vn, so that one, sorry, so 5 over 2n squared plus 1, then our vn is n squared, so we have n squared over 1, so that we have those. So this is limit of 5 n squared over 2n squared plus 1. If you take a limit, n goes to infinity, yeah, n goes to infinity, take a limit, n goes to infinity for that, so that gives us 5 over 2, which is positive. Alright, since 1 over n squared converge. So for the second comparison test, we have if the limit of ratio between un and vn is one of them converge, then the other one also converge. Is the other one diverge, then the other one also diverge. So in this case, we have our vn converge. So therefore, the other series, which is the one that we want to test, 5 over 2n squared plus 1 also converge. Okay. Some more example. Before I go to the proof of the theorem, so let me give some examples so that we get familiar with that. N cubed plus 2. Let's try this one. So by looking at this, the best choice is 1 over n. Okay, the best choice 1 over n, because the highest order of for numerator is squared. The highest order for the denominator is 3. So just you can cancel out. So we got 1 over n. So this is our choice. If you write this n squared, now look at the denominator. So we have n cubed plus 2. This is greater than n cubed, correct? So if we inverse, so we have 1 over n cubed plus 2 less than 1 over n cubed. Okay. If multiply by n squared, so we have n squared over n cubed plus 2. So this is what we want, that less than n squared over n cubed. Right hand side, this is equal to 1 over n. And we know that this series 1 over n diverge. Okay, now what does our test say? Our test say is that if un less than or equal to vn, and for the divergence, so I mean the smaller series diverge, the bigger series. So we need un. This un diverge, then our vn diverge. So by looking at this, does it satisfy those inequality? Does it satisfy this condition? So look at this. If the smaller series diverge, the bigger series diverge. So look at this. The smaller series less than the series that we know the property which is diverge. So it's opposite with this, right? The inequality is opposite. Supposed to be that less than. If we have less than, then we can say this is diverge. But in this case, cannot. Okay, because it's not satisfied the condition given here. So for this case, we cannot make any conclusion. Okay, no conclusion can be made. No conclusion. Then how? We can try other tests. So let's try the second comparison test. Second comparison test say the limit of un over vn equal to some number L positive. If any of these converge, then the other one also converge. If the other one diverge, then the other one also diverge. Okay, so we use that property. So if we choose, let's say our vn is 1 over n, so let vn equal to 1 over n, and our un is the one that we want to determine, which is n squared over n cubed plus 2, and we take a limit. So we have un over vn, so we have n squared over n cubed plus 2 over that, so just n goes to infinity, so that we have limit n cubed over n cubed plus 2, n goes to infinity. So this gives you 1 which is positive. So it satisfies our theorem. Yeah, satisfy our theorem. Satisfy our theorem means we have some numbers there, and those numbers are positive. We have numbers 1, and those 1 is positive. So therefore, and we know that since 1 over n diverge, okay, I use that symbol as a diverge, therefore we can make a conclusion that this series n squared over n cubed plus 2 also diverge. Okay, so I hope that it will give you some idea on how to determine the behavior of the series, either converge or diverge, with those two tests that we have, first comparison test and second comparison test. Now let's see at the example. I give you one more example. Let's say if I have 1 over n log n. Sorry, just that 1 over n. 1 over log n. So we know that log n is less than n, correct? So we inverse this, 1 over log n greater than 1 over n. And this series, 1 over n, diverge. The smaller series diverge, the bigger series is also diverge. So therefore 1 over log n also diverge. Can you try this as an exercise? 1 over n log n. Let's just try, see what happens. Okay, and in the note we have some more example. I think I don't have to go that detail there. Okay, I'll give you one more example. Let's say we want to determine that series. N plus 2 over n plus 1 square root n plus 3. Okay, so for those terms, n plus 2 over n plus 1 n plus 3, this is bigger than, this is n plus 1, this is n plus 2, this is n plus 1. We try to cancel out that. Is it possible? Yes, we can reduce that one. So greater than n plus 1. So because if you close that, we have n plus 2 is greater than n plus 1. That's correct. And then just fix the denominator. So we have n plus 1, n plus 3. Okay, so that cancel out. What left is that. So we have 1 over third n plus 3. And of course, n is less than square root n is less than n. Okay, if you inverse 1 over square root n greater than 1 over n. So in this case it will be greater than 1 over n. Yeah, for certain n, of course. So the smaller series diverge. Yeah, 1 over n diverge. The smaller series diverge. So the bigger series is also diverge. So therefore, we can make a conclusion that n plus 2 over n plus 1 n plus 3 also diverge. Okay, so I'll stop here for this video. Let me recap. The important thing is that if you have three things, 1, 2, 3. Okay, the first one, if un less than vn, and that un converge, yeah, the smaller series converge, then the bigger series also converge. Okay, so in this case, this is the one that we want to determine. This is the one that we already know the properties, which is converge. The other one we have, if un less than vn, and the bigger series, sorry, this is, okay, so the smaller series, so that one is converge. So the bigger series diverge. I think I make mistake here, is that? So un converge, no, should be here, vn, sorry. The bigger series converge, then the smaller series converge. Okay, if the smaller series diverge, so un, in this case this is un diverge, then vn diverge. So the other one is, we take a limit of un over vn, give some numbers positive, then both un vn converge, or un vn as a diverge, or this one converge together. Okay, so we have three tests for the moment. So I stop there for the moment, for this video. Thank you.